SwayamPrabha. Digital India. Educated India.
So, today we will continue our discussion on flow mode analysis using Bingham biplastic model. This was the Bingham biplastic model that we discussed, and then we saw that this kind of model divides the entire region into several parts. So, at the center there is the plug region where the shear strain rate is 0, and then at the two sides of it there is a region where the shear strain rate is the magnitude of the shear strain rate is less than gamma t dot, and then beyond that there is a region where the magnitude of the shear strain rate is more than gamma t dot, and we are analyzing only half of it, half of the domain because of the symmetry. So, in the last class we found out the flow velocity equation in region 5. Today we will continue from that. So, we will find out the equation of velocity in region 4. Now, in region 4, the equation of shear stress is tau y equal to minus of tau y plus mu 0 into del u 4 by del y. So, u in region 4 is denoted as u 4, and that is equal to minus del p by L multiplied by y. Now, from here we can write del of u 4 by del y equal to tau y minus del p by L into y, and then we can integrate the equation, and that gives us u 4 equal to tau y. So, there was a mu also here, mu 0 which was missing. So, after integrating we find tau y by mu 0 into y minus del p by mu 0 L multiplied by y square by 2, and then we have plus C 2. Now, we have to evaluate the constant C 2, and that we can evaluate it by putting the condition that in this region, in this dashed region, the junction between region 5 and region 4, the velocity obtained from the equation that we are dealing with now is same as the velocity that was obtained from the that can be obtained from the velocity equation for region 5. So, the velocity is continuous between junction 5 and region 5 and region 4. If we apply that condition, so that just can be written as u 4 at y t is equal to u 5 at y t. Now, if we apply that condition, then we can evaluate the constant C 2, and after evaluating the constant C 2, if we put it back in the equation, so this helps us evaluating C 2, and then after evaluating C 2 we can find out our u 4 y as y minus y t by mu 0 multiplied by tau y minus del p by 2 L multiplied by y plus y t, and then we have plus y t minus d by 2 divided by mu 1 multiplied by tau I plus mu 0 minus mu 1 into gamma t dot plus y plus d by 2 multiplied by minus del p by 2 L. Now, that becomes our expression for u 4 y, and then we know that y t is equal to mu 0 gamma t dot multiplied by L by delta p plus tau I multiplied by L by delta p. So, we can put this here and here also, and if we do that, then we can find out our okay. So, we can put this y t here as well as here, and then if we, after doing that, our expression for u 4 y becomes just this 1 by mu 0 multiplied by tau y minus delta p divided by 2 L y multiplied by y plus 1 by 2 mu 1 L multiplied by delta p d square by 4 minus L d into tau I. We can put another multiplied by tau I plus mu 0 minus mu 1 into gamma t dot, and then plus L square by delta p multiplied by tau y plus gamma t dot mu 0 whole square of it, and then 1 minus mu 1 by mu 0, and that is the entire expression for u 4 as a function of y. Now, we want to look at the plug region, and in the plug region we know that the velocity is continuous. So, whatever the velocity as u 4, whatever the velocity that we get at y equal to y yield, that means here whatever the velocity we get at y, that means here the junction between region 3 and 4, based on the velocity equation at region 4, that same velocity is valid throughout the entire third region. So, we can say that u at region 3, we have u 3 as a function of y is just u 4 that is obtained at y, and we know that y is equal to delta of 2, which is tau y L by delta of p, delta p, and then y 3 becomes tau y square L divided by 2 mu 0 delta p plus 1 by 2 mu 1 L multiplied by delta p d square by 4 minus L d multiplied by tau I plus mu 0 minus mu 1 into gamma dot, and then plus we have L square by 4 p multiplied by tau I plus gamma t dot mu 0 whole square of that multiplied by 1 minus mu 1 by mu 0. So, that is our u 3, and that is the constant velocity that is valid over the entire third region. Then what we can do is we can do some non-dimensionalization. So, for that again we can write delta dot as delta bar as delta by d, and then we define delta t as a new variable which is just twice of y t, which means delta is this region, this dimension from here to here, whereas delta t is the dimension from here to here, the distance between here to here. So, the distance between the junction of region 1 and 2 and the junction of region 4 and 5. And then again we can further non-dimensionalize delta t as delta t bar equal to delta t by d. So, after all this we can write u 1 as a function of y in a non-dimensional form as delta p d square by 8 L multiplied by 1 minus delta t bar square divided by mu 1 plus delta t bar minus delta y. And so, these are the non-dimensional terms that we will be using. Now, with this these velocities can also be written in a non-dimensional form, and we will not do that. So, after that we will find out the equivalent damping coefficient, and for that again we have the same approach. We first find out the total flow rate, and then we equate that total flow rate with a flow rate which would have been there if there was a uniform velocity um, and that would give us equivalent uniform velocity um, and then we divide that velocity by the force, and that would give us the damping coefficient. So, for that the first we have to find out the total volumetric flow rate. So, total flow rate Q is equal to Q Q1 plus Q2 plus Q3 plus Q4 plus Q5, and from that we can write this as and we know that Q2 and Q4 are same, Q1 and Q5 are same because of the symmetry. So, with that we can write our total flow rate. So, we can write this as 2 multiplied by y t to d by 2, and we have b um dy. So, if we again look at the diagram, it is between y t and d by 2 where um is valid. So, the corresponding flow rate is just um multiplied by b integrated over the region, we multiply this by 2 because of the symmetry, and then we have 2 and then a region from y y to yt, and this we can, here we can integrate b u4 dy, and then we have 0 to yy, and here we integrate just b multiplied by u3 dy, because 0 to yy is half of the plug thickness. So, if we just multiply by 2, we get the total flow rate due to the entire plug thickness, and here u3 is constant over the plug. So, we can just multiply by the thickness of the region, and that will give the corresponding flow rate. So, after doing everything, the total flow rate comes as delta p, then we have b d cube by 12 mu 0 L, then 1 minus delta bar y multiplied by 1 plus delta y bar by 2 minus 1 minus delta t square. So, here delta y is y bar is just our delta bar, because that is defined between the region yy and minus yy. So, we can call it delta y bar also, and then we have 1 plus delta t bar by 2 multiplied by 1 minus mu 0 by mu 1, and that is our total flow rate Q. And then we equate that to an equivalent the total. So, this gives us the total flow rate, and then we equate that to flow rate that would have been there because of a uniform velocity u_m. So, we equate this Q with u_m bd, and from there we can find out u_m, and also we have the force F is equal to delta p multiplied by bd. So, now if I divide F by u_m, that gives me the effective active damping coefficient. So, that becomes our delta p bd divided by q by bd, and if we do that, finally the active damping coefficient comes to be 12 mu 0 L into our b square d square divided by bd cube, and then we have here 1 by 1 minus delta y bar whole square into 1 plus delta y bar by 2 multiplied by 1 minus delta t bar whole square, and then we have 1 plus delta t bar by 2 and 1 minus mu 0 into mu 1. So, this is our equivalent damping in the active mode, and then we can find out the effectiveness of this active damping by dividing that by the active damping in the inactive mode. And for that we can just find that out by Ceq divided by Ceq A divided by Ceq 0, and that again using the same approach comes as 1 just as 1 by delta 1 square multiplied by 1 by delta y bar whole square multiplied by 1 plus delta y bar by 2, just this denominator should come here, multiplied by this into 1 plus delta t bar by 2 multiplied by 1 minus mu 0 by mu 1. So, what we are doing here is to find out the inactive damping, we are just setting these terms delta y bar and delta t bar to 0, because when the fluid is not active at that time we do not have the concept of yielding. So, the constitutive relation is just that of the Newtonian fluid. That means that region does not get divided into plug, or the region where the regions 3 and 4 does not come into picture, the entire all these divisions does not come. So, the entire region has just one constitutive relation, which is mu into the shear strain rate. Now, because these quantities are 0, so Ceq at 0 is just this. So, if I divide this quantity by just this, we have this as the, so if I divide this quantity just by this, so we have the Ceq active by Ceq 0 as this. Now, so here we can see that because the constitutive relation is piecewise linear, here our this damping coefficients does not depend on the velocity. In the previous case, when we are dealing with Herschel-Berkeley model, there the constitutive relation was non-linear. So, because of that the equivalent damping coefficient was a function of um. Here it is piecewise linear. So, here we do not have that as a function of um. So, with that I would like to conclude this lecture here. Thank you.